Thinking I should bring this home and say, here you go dear, I got you a chocolate. That is something I would do, I assure you. Lee, come on in.
Hi.
Where the fudge is my Valentine's present? She didn't get me one.
I should get you one.
Of course. Alright. Have you got the question there? Okay, can you open the question so you can give me the info, please?
Wow, thank you.
I'm the only one on now.
I'm going to eat this later because today's the first day of Lent. Do you know this?
Yeah, for everyone.
Thank you. Well, you can hold and just give me the info. Do you know this word? Monica, you know this word, don't you? Yes, well, not just fasting. So, here, this is a time where people give up one thing they like for Lent. So most people would stop smoking.
Before Easter.
Before Easter. Yeah. So what I'm trying to do is not to eat in between meals. Do you know what I mean?
But it's not a bit too late.
No, you see, this is day one. This is day one, and you're tempting me on day one. So I will eat this. I will eat this after my lunch.
And that's still a bit meal.
No, after lunch, like the dessert of the lunch. All right. What's the first question there, Andrew? What do I tell you?
Okay. Diffraction grating has 300,000 lines per meter. Red line with wavelength 633 nanometer is incident shown normally on the grating, which is 1 meter from a screen. So, A.
Yeah.
Determine the line facing D.
Okay, the D. So, did you know what to do to get the D here?
1 over 50.
1 over 300,000. Yeah, because it's 300,000 in a meter. So how far apart are they? That's 1 meter divided by 300,000. What is that number?
3.3 micron.
Okay. B. What's the B part, Andrew, please?
Determine the diffraction angle for the second order of red line.
Right, so that's using the formula n lambda equals d sine the theta is what we want. Yeah, we're happy with this. So sine theta is sine inverse 1266 over 3.33, and then this is 10 to the minus 9 divided by 10 to the minus 6 is 10 to the minus 3. So it's whatever sine inverse of 1.266 over 3.33 is. What is that? Could you put that out for me, please? 22.3 degrees. Yeah. Okay, C. Is it not?
Yeah.
Is it? No, wait, hang on. There's a problem in the matrix here. Is this right or not? It was you that made me sick. I have the exact same cough. It's not your fault. No, don't try to hide it. It is? Okay. What's C? Go ahead.
Determine the highest order diffraction.
Okay. So this is the one where the theta can be at most 90. So you have n lambda, equals, or rather I kind of like to say is less than d sine theta, and the sine theta being sine 90. So what the fudge was the G? Here it is. Okay. So the n has to be always less than whatever 3.33 over 633 10 to the minus 6 that's 10 to the 3, so that's 3330 over 633, and also n has to be a natural number which is less than this. What does this work out to be? 3330 over 633? 5.26. So the maximum n can be is a 5. Yeah.
So Steven, so
Yeah.
n lambda equals d, right?
Basically, yeah.
Yeah, so n equals d over lambda.
Yeah.
So
Now I prefer to say n has to be less than this.
yeah, whatever. So
Whatever. Okay.
0. What is d? 0.003 nano.
Yeah.
Nanometer over lambda. 6
Yeah.
nanometer.
Yeah.
Why do I get different?
It's treating micro.
Well, you said micro, didn't you?
Yeah, micro.
Micro over nano,
Yeah.
didn't you? D. What's the story in D, Andrew?
The red light is replaced by a blue light of wavelength 506.4 nanometer, and it is found that the differential angle for
Okay, pause. So this is the hard one. Yeah. This came up one year, and I was looking at it going, woohoo, it's hard. But then actually when you see it done, you're like, oh, the hard part is understanding what the heck they're talking about. So what's happening here? What colour was the light to begin with?
blue.
Right.
Red.
Red to begin with.
Yeah.
So it comes in, the red, and it hits the diffraction grating, and it makes that's 0, that's -1, -2, that's 1, that's 2. Okay. And then the blue one comes along, and the blue one, because it's a different wavelength, it won't have the same positions, because if you remember the formula, n lambda equals d sine theta, increase in the wavelength would cause a bigger angle. Is the blue a bigger or a smaller wavelength? It's a smaller, so the blue shouldn't spread out as much. So just as an example, maybe the center will still be here, but maybe the next one is here instead. Do you know what I mean? And maybe the next one here is here. It's not quite lined up. But I said at some point, say up here, the red and the blue are on the same location. And not only that, I also tell you that the difference in the order is 1. So for example, you notice how the blue one and the red one, they're not quite lined up, but here they will be lined up. And I don't know where here is. And I also tell you the difference in the order is 1. So for example, maybe the red is the 4th order and the blue, that'll be the 5th order for the blue, and they'll be lined up. Yeah. What precisely do I say about the order, just so we're 100% clear?
Use x and x plus 1 for the order.
But what did I say before that about the order and the 1?
Oh, okay. It is found that the differential angle for some order of the red light coincides exactly with the differential angle for the blue light in the next
order, yeah. So if this is order x, then this will be order x plus 1. Okay. So you have two formulas here. You have, for the red, x lambda for the red light equals d sine theta. And then for the blue, you have x plus 1 lambda, the blue light, that's equal to d sine theta. But if these coincide, it means that the sine thetas are the same angle. And of course the d is the same. It's the same diffraction gradient. So in fact, you end up with this nice result: x lambda red equals x plus 1 lambda blue. And so the x's solvable. You get x lambda red equals x lambda blue plus lambda blue. So you get x will equal lambda blue over lambda red minus lambda blue. What's the wavelength of the blue? 506. Oh, so I did something wrong. Yeah, no, it's okay. Yes, 506.4, and then this is 633. Now, why am I not putting in the nano? Because nano's in every quantity here, so it cancels out. Now, because x is an order, we should get an exact number here. I mean, an exact natural number. Any rounding? Right. Right. I picked the right decimal point. Yep.
So for blue,
So blue actually would be, so the red one would be at the 4th order and the blue one at the 5th order. These are actually the same point on the screen.
by the way,
Yeah?
I could be 0.0003 only, not 3333.
Ah, that caused the rounding. Yeah.
Yeah, here.
That's fine.
Yeah, fine.
That's fine, yeah.
Fine.
Well, in the exam don't put more decimal points, but
Well, my calculator shows only 0.03.
no. I bet your calculator, type it in again. Now don't look at the screen, but type it in your calculator, and I bet your calculator will have this on it. Oh, you're looking. Where is it? I can't even see. Ah, disgusting. Why did they do that? I'm very sad. That's supposed to be a super calculator. Now take out the Casio and type in the same thing. This learning experience is brought to you by Casio.
No, that was.
I what?
No, I'm
Champion!
I'm a half time.
That's very interesting. Can I see? Just make sure there's nothing on the screen that tells you.
If something is behind the point, then it is like, what is that? So, first half is there, but it's not there.
1/300.
I was thinking of starting a blog. I think I'd like this to be my first blog post. Can you take a picture of the screen and send it to me?
Okay.
I'm going to make it my first blog post. I'm going to call it something like a graphing calculator. Are they all that? Are you looking at me like that? Okay, next one. Do you have a blog?
Yes.
You do?
I know.
What's it like, monicasays.com or?
It's not special.
No? Alright. Oh, is this where you like dish on your teachers or something? And use a fake name? I'm Shmonica. Then go to S. Yeah, although the S wouldn't work for. And I have this teacher, Stephen. Oops. Alright. E. What's next, Andrew?
Okay, determine the diffraction angle for second order of blue light.
Ah, that's boring. Do you really need me to do that one? It's the same as the earlier one. Oh, what did you get, by the way, for it? What is it?
No, 7.7.
I can't hear you. 17.7? F. D.
The fringe were red in part A, and then of course blue in part B. If the blue light was replaced by white light, what color would the fringe be?
If it was replaced with white light. In other words, my question is you put all the different colours in it. Now, you kind of see what's happening here. For the red light, the second order, what angle was it? 22.3 for the red, and the blue was. So when you put all the colours together, you'll get. Come on in. Who's that? Is that Sean? Jerry.
Hello.
Why are you late, Jerry?
I woke up.
Ah, Jerry. Where's my present?
Here's your present.
Valentine's Day. You didn't give me a present?
Valentine's Day.
Oh no, I don't have enough. I think I just got here.
Anyways.
We don't have enough time. Oh, take a joke. That's for me.
Yes, it's for you.
Oh, thank you.
Yeah.
You just show me.
And who's this now? Come on, why are you late too? Yeah, but what delayed you guys? Oh, come on, sit down.
What is it?
Okay, he's ready. Were you printing all this time?
Yeah. Almost 1 hour.
Oh, what happened?
I cannot log in my account and meeting. So I have.
You saved him.
Yeah, it's
Saved you, okay. So, as we can see, as we increase the wavelength, what happens? Oh, sorry, as we decrease the wavelength, what happens? The angle decreases. So, remember the wavelengths go in the same order as the rainbow. So you have red, then the next in between blue is orange. So in fact, yeah, so the orange and yellow wavelengths, which are in between red and blue, their angles will also be in between red and blue. So in effect, you get all these colours here: red, orange, yellow, green, blue, indigo, violet. All these colours here close together because there's not much of a difference here. So basically, the fringe patterns look like little rainbows.
Isn't it white?
Yeah, it's white, but white is a combination of all the colours, and the different wavelengths get split with different angles. Do you know? We just calculated how the angle is different for the blue and the red. It's different for all of them, but the difference is such that the colour in between red and blue, their angle will be between the red and the blue as well. In other words, they'll be in the same order as their wavelength, meaning you'll get a rainbow.
So the answer is between red and blue, all the colors, right?
No, all the colours between red and purple. The rainbow, the full rainbow.
Oh, full rainbow?
Full rainbow. No, I was just using that as an example. You get the full rainbow
Oh.
on each of these. Yeah,
Why?
I just explained why.
But
Huh?
But isn't there nothing between red and blue trying to...
No, there is. It's continuous. There's a colour between every colour. It's a spectrum. We have this idea that there's only 7 colours, but that's not really true. There are many, many colours. Does anyone know the reason why it's decided, or we call it 7 colours of the rainbow? When you think about it, there is a colour between red and orange. It's a sort of reddy orange, you know. Why do we say only 7?
Basic.
Yeah, but why 7? Why not? Like, I mean, I could have given a name to the colour in between red and orange and could have called it 8 colours of the rainbow. Or I could have just said red, green and violet. Is it the 3 colours? Because, you know, you can have as many as you want. It's continuous. So why 7?
Basic color.
Lucky number.
You're actually quite close.
Oh.
No, his answer of it being a lucky number is quite close.
Oh. 777 jackpot.
It's not gambling related. It's just one of those religious things when people were first given names to the colours of the rainbow, because people believe that rainbows came from God, it must be perfect, and 7 is the perfect number. So it's just 7 for that reason, which is close to your answer of being lucky.
Yeah, even the 9.
You could have any number.
White and black.
Yeah, you know. So, Chrissy, there's colours in between the colours. Alright, is there a G or?
Yeah, we have H too.
Oh, nice.
And what is the fringe spacing for the red line?
That's the x, isn't it? Which is lambda.
Is S.
Huh? Oh, sorry. I used the letter S. S equals lambda.
D. Or.
This way around? Yeah. For which color, Andrew, sorry?
Red.
Red, which is 633 nano. And the D is 3.33 micro. And what's the distance between the... 1 meter?
Yeah.
Nice. Right, so what did you get here? 0.19 meters? So 19 centimeters then. Okay, H?
How wide does the screen need to be?
Which color of all the colors is the furthest out? Red. So we need to make sure that all the reds can fit, because if the red can fit, then all the other smaller wavelengths will fit as well. And we've already worked out the maximum order for the red. It's 5. So does that mean the screen needs to be 5 times 2 times 19 centimeters, which is 1.9 meters? So you don't want just, like if you were doing this in real life, you wouldn't use 1.9, because then that means the last fringe is right at the edge. You want to give yourself a little bit of space. So I might actually say use 2 meters would be a suitable number to use.
So why times 2?
Because it goes 0, 1, 2, 3, 4, 5, but it also goes down to -5. In the exam, the answer, guys, in the exam the answer would be 1.9, but of course in real life it would be silly to use 1.9, because why would you make your life difficult by just having exactly enough? You might as well put a few centimeters on the end. Yeah. Is there another question now? So that's the interference. What about the which one?
We have to number 6.
That is what was that one about today?
The length of the wave equals the length pi plus.
Oh, the M correction. Yeah. Okay. What number is this? 6. Right. Go read the info, please, Andrew.
A standing wave of frequency 1100 Hertz, which is third harmonic, is formed in the open and one-end pipe. Likewise, a fifth harmonic standing wave is formed at a frequency of 1800 Hertz. There is a small error in estimating wavelengths from the frequency. That is it length?
Yeah.
The length of the wave equals the length of the pipe plus.
Great. I think I got the whole info here. And then my question is, what's the end correction?
The delta.
The delta L, which is the end correction. Yeah. So what's happening in this picture? This is the third harmonic, which is 3/4 wavelengths, and this one is 5/4 wavelengths. So what's happening is 3/4 of a wave. Goodness, hang on. This is vibrating, this antinote, and this is 5/4 of a wave. Close enough. Now, yes. Now, if you look, you know the formula V equals lambda F. So if you were to use that, you would say, here I get 340 equals, and we'll call the pipe's distance here to here L. So the wavelength would be 4/3 L. Yeah. So I think this is okay. No, by F.
Oh, by F.
Yeah.
Oh, yeah.
equal.
Yeah, the L equals 3 over 4 lambda. Yeah, so the lambda is 4 over 3. And then here you would say 340 equals 5 over 4 L times 1800. Now, huh? Oh, goodness. Thank you. Now there's a small problem. You might say, well, that's strange. Why did I give you 2 pieces of information when it looks like 1 is enough? And actually there's a further problem. If you calculate the L from each of these, you'll get different L's. But of course the L doesn't change. So what's happening is, we are saying, if I go over here, I just go back in time. Here we're saying that the wavelength is, what did I say, 4 over 3, the length of the pipe. But actually it's not really, because the wave sticks out a little bit on the top. So the L is actually a little bit too small. It should be a bit bigger. So it's not quite the length of the pipe we need to use for whatever the true length is. And we don't really know what that is because it's sticking out a little bit from the pipe. So we'll have to say L plus a small extra L, which we have no idea what it is. And likewise here, the wavelength will be 5 over 4. Again with the L plus delta L. Now, if we use our formula, I get 340 equals lambda, which is here, times 1100, and here I get 340 equals 4 over 5, L plus delta L, 1800. Okay, so if you look now, you realize, hey, I've got 2 equations with 2 unknowns. I can solve this. So if I just bring this up, I get L. Something's wrong. No, everything's okay. No, everything's wrong. I think I put my L on the wrong place.
Isn't it?
I should be outside of this, shouldn't it?
Wavelength minus.
And the L is the length
I
of the wave.
like
Like lambda is 4 over 3 length of the wave, which is length of
Oh, I did it wrong here. Let's go back in time again. Okay. Go ahead, what were you saying, Monica? Lambda
is 4 over 3 length of the wave.
of the pipe.
Of the wave.
Huh?
Like if L is equal to.
Why you call it L in the picture? L is the length of the pipe. And the true length we should be using should be this.
Length of the wave.
Well, it's not one way.
If you add those two, it equals to the length of the wave.
Well, it'll equal 3/4 the length of the wave. 3/4 the length of the wave.
The wave that you have in the team.
I'm confused.
Okay, this thing you wrote for us, L wave is equal to L5 plus delta L.
What did I write for you? Yeah, that'll help me.
Length of the wave is equal to length of the pipe plus delta L.
Oh,
Here.
length of the wave equals the length of the pipe plus delta L. Yeah.
I'm just saying L wave.
It's correct. What you wrote?
What I just wrote? Or what this is?
What you have already erased.
Okay, no, that's okay, it doesn't matter. I can write again. But I need to get the lambda in. So what is the lambda? This is 3/4 lambda? Yeah. Okay.
You can find the lambda for
Can I?
you have frequency and B.
But I don't. I have 2 unknowns here.
The lambda. You have F.
Oh, you're saying this equals what you call it?
Frequency over F. Which you have.
3/4 V over F.
Yeah. You can find the wavelength for both of them.
Something feels wrong.
Yeah.
Find the wavelength for both of them.
Yeah, for F2 F1 using V over F.
Interesting.
Same now.
I don't like that way. It confuses me.
Can we just use error correction a wavelength because
Yeah, I think that would have been better. Let's write this down again. Okay, we have two equations. So V equals lambda F. V equals lambda F. So this is 340 equals the wavelength times 1100. And here, and of course there's something strange here. This one is 340 equals the wavelength times, 1800. Now, what is the wavelength if I want to use it in terms of the pipe?
Over 2
Oh goodness. Yeah, the lambdas are different. Yeah, they're not the same. Yeah, because this lambda will be smaller. Yeah. So, anyways, this one here would be 4/3. Yeah. 4/3 length of the pipe plus delta L. And the only thing I'm thinking about is, do I need to put brackets around this or not? I do.
4/3 delta
My question is, what I'm trying to think in my head is, do I need brackets here or not?
L. I think you have to.
I think, yeah, that's what I'm thinking, I have
The
to.
lambda.
He's right, I think so. So this one here would be 4/5 L plus delta L. This is what I got a minute ago, but something deep inside me saying this isn't going to work out. Let's see, but I have a vision now in 1 minute's time that we'll get a problem that doesn't give us an answer, because I don't like something about this. I suppose there is only one way to find out. Okay, no, I'm not. I can see what's going to happen, because what's going to happen is I'm going to bring this under, bring this up, bring this down,
yeah.
bring this down, bring this up, bring this down, and I'll have two equations with the same coefficients. No, the problem is there is no brackets.
Yeah, that's what I
No, you didn't.
No, I said no bracket. You say it's breaking.
No, that doesn't sound familiar.
But what?
I wasn't clear in the question, and because I wasn't clear in the question, I wasn't clear in my head. But the reason is that the error is, and I think this is what you were trying to tell me. Perhaps this is what you were trying to tell me. The error is on the wavelength, not the L. So in the question, I shouldn't have said delta L. It would have been a bit better to say delta lambda. The error in the lambda. So this is like lambda plus delta lambda.
Please.
Yeah, but you didn't say it clearly enough.
And I use rather than delta lambda, I use just E like F.
Ah,
It's easier to see.
and that avoids every problem. Yeah. So I need to change the question so that instead of saying L and delta L, I say lambda and delta lambda. Now I can get a solution. That over that equals this, and this over this equals this.
Yeah.
Look, there I go again. Delta lambda. Delta lambda.
What?
I need to get it clear in my head that the error is on the wavelength, not the length of the pipe. Because you can measure the length of the pipe exactly. I should have been saying the error correction, the E, is on the measurement of the wavelength, not the measurement of the length of the pipe. Okay, let's solve this. Right, mode 51. Okay, 4 over 3, 1, 340 over 1100. 4 over 5, 1, 340 over 1800. Okay. So the L is 22.5 centimeters, and the error correction in the wavelength is as small as it should be, 8.59 millimeters.
Teacher.
Yeah.
But the equation doesn't make sense. You are saying 4 over 3 L plus delta lambda, but the whole thing is only 4 over 3 lambda.
Say what?
I mean the logic stuff you're saying 4 over 3 L, which is the actual wavelength, plus another lambda. But the whole thing is just 4 over 3 L.
I suppose the thing, yeah, just to be really clear now at this point, there's 3/4 in here, like this. So we're saying the L is roughly equal to the 3/4 the wavelength. Or in other words, the wavelength is roughly equal to 4 over 3 L. Well, that's the basic idea. But we have a little problem here, because if we do that, there will be a small error on this. And the appropriate thing to do would be to say that this equals 4 over 3 L plus, you just called it error, which I was calling delta lambda, because maybe I should just not call it anything, just call it error. I'll call it EC for end correction, and then we can stop trying to picture it. I think that'd probably be the safest thing to do. They see you're picturing it. I can see you. What? No, keep it away from me. Okay, Chu, can you hand me that, please? No, her book. Let's see. So you got two different distances. What are you doing? What the? I suppose that's okay. What you're doing, Monica, basically what you're doing there, the way Monica's doing with it, which is another way to do it, we'll just leave that for a moment. What you could do is just forget about the error. Just forget about the error for a moment, and you have V equals lambda F. so you get V over F equals lambda. So for the first one, you get V over F, and the lambda is, so that'd be 4 over 3, the length of the pipe. And then for the second one, it's V over F equals, what is it, 4 over 5? Yeah, 4 over 5, the length of the pipe. So in the first one, Monica, you have the answer there when you put the numbers in. L is 3 over 4 V over F. This is for the first one. And what answer did you get, your first length? 0.2318 meters. And if you do the same thing for the second one, what is it, 5 over 4 V over F, you get 2363 meters. Now, of course, you should get the same answer. And what we'll learn about in when we're preparing for the labs is that when you have, two answers, the true answer will be the average from your experiment of all your results, and the error is the difference. So, if the true value is in the middle somewhere, then the error would be, I would say, the bigger number, 2363, minus the smaller number, over 2. Now, can you just hit that in, and can you all type that in, and let's see what we get here. That's a 2. 2363. 0.0. Is that what you got?
Yeah, 2.25 times 10 to the minus 3.
So it's not actually the same as this then.
Yeah.
Is that what you got? What answer did you get for your error? Oh. Anyways, I don't think this one would be good then. It's not giving me the same answer. I think the reason that it's not working is because in both cases here, it's the same type of error. In chemistry, you're preparing your lab reports. You know systematic error?
Yeah.
Yeah. Both the errors here are systematic errors. They're not random errors. If they're random errors, then you can do what I just did here. But now that I think about it, these are systematic errors. The same errors happen each time. It's making the wave longer than it. There's an extension. It's a bit like in the chemistry on the weighing scales. If you don't have it set to 0 at the beginning, you're adding the same error each time. So I don't know, Monica. I would prefer if you did it this way. Now there is another way to do this which is not on the course, and you can't do it here anyway, but believe it or not, it has to do with the thickness of the pipe. I can't remember exactly what it is, but it's something like, if you knew the diameter here, you can work out quickly what the error will be, the end correction, because there's a relationship between the diameter and the error.
Why?
I don't even think there's a clear reason why, actually. I think if you go to Wikipedia and look up end correction, there isn't a clear explanation. So the explanation I gave was the wave is a little bit out of the pipe. Yeah, but like, why is it a little bit out, and why should this affect it so? So I think this is why it's not on the course. It's a little bit tricky. Remember I said I don't think he'll ask you this question because it's not actually one of the learning outcomes in the syllabus. But it has come up on the exam twice before, so just to be safe. Yeah. Cool, dudes?
Yeah.
I need to remember to change that question. Let me add that to my to-do list. Just take out my iPhone here. Wikipedia explains it, but you also see in the article when it gives you the formula for the end correction, it says there is no established formula for the end correction. Change. Yeah, but that. No, I know. I know a formula exists. I'm not saying a formula doesn't exist. Okay, fine. Change length to wavelength. No, I see my website is running off of a Raspberry Pi 2, and I just bought a Raspberry Pi 3, and I think I'll use this as a time to rebuild my website from the beginning. For what? Oh, you're confusing me. Physics. He knows what it is. And save. Right. Any other tutorial questions?
Do you have a tutorial question? Do you have Adam prep today?
No, we thought it's the same. It's the same thing every week. I told you the exam prep will start after the break.
Because they cancel group tutorial in the timetable, but they don't do the same for the exam prep, so that's all. I mean, they cancel group tutorial now.
Every week it's the same thing from them.
That's
Do we have exam prep? And every week I say no after the break. And every week you say yes, we'll start the exam prep after the break. That makes sense. Okay. That's the tutorial part finished then. That should answer all your questions. We shall celebrate. We shall look at what the wave questions look like in the exam. So let's have a start on that now. Actually, I shouldn't stop the recording. Okay. Let's see. Yeah.
It's after class. Why proton and electron doesn't coincide? Doesn't
Well, that actually has a complicated answer, which I remember. I think this is called the stability of the proton and the electron, and the reason I'm afraid to tell you involves quantum mechanics. So I remember doing the proof in third year in university, and it's like, and that is why, like to answer your question. And so it's one of those physics proofs that's just a long maths proof. You do the calculations and then you see, this is the reason why. But you need some physics that you haven't studied yet, which we'll do a little bit of in the atom section. So we can kind of give you a bit of an answer, but why it's so stable is actually an interesting question.
No, I can see it.
Lee!
Yeah.
Lee! Don't make me come down there. Physics. Jerry! Be good. It's Valentine's Day. Right.
You don't have a friend?
I don't need a break. I did all the work. Okay. Mechanics, materials, electricity, fields, atoms. Mechanics, electricity, atoms, fields, here we go, waves. Yeah. Okay, children, let's start. this is the experiment we're actually going to do. Describe an experiment that could measure the critical angle of glass. I'll give you a minute, and then I want you to tell me what you came up with. There's 4 marks. So when you're writing your answer, there's...
You have to label it.
Well, usually in the marking scheme, they just care about the points you have to make. So, for example, no, I said usually. However, in this one here it says with the help of a diagram, so you can draw a picture. What you need to do is to think about how you could measure the critical angle of glass. Wasn't it glass? Yeah. No, don't eat. Well, once you give me an answer, then you can have your treat.
Do you have to say something?
Of course you have to say something, KJ. You can't say nothing.
1 over...
Okay. I think really for the first part, you need the diagram. The diagram will help. So you should have something like this. This is air. This is glass. And then you should have here something like a laser. And then normal, and you want the laser to run along here. And then what else would you need? You would need a protractor, something to measure the angle. No, sorry, 0 here,
Sure.
90 here.
You need the laser shoot from the glass to the...
I'm sorry, thank you. Oh well, I'll just change those around. Yeah, it's the glass to the air.
Why?
You mentioned different things.
No, you can only ever get a critical angle when you go from a more dense to a less dense material. Yeah, thank you. Right, so this isn't going to be enough marks. You would need to put down some steps. So you would say, place the laser at 0 degrees for I, and this angle here is I. Yeah, and then 2, increase I until or equals 90 degrees. And this angle here, this angle here is or. And then step 3, the critical angle is equal to whatever the I was to make the 90. There's a very simple experiment. Yeah. Right, there's other ways to do it. This is the easiest way I can think of. There's actually more accurate ways to do it. The way we'll do it is that there's a different way to this.
You want the lab?
Yeah, this we'll do this in the lab.
Oh, that's a part of the lab, right?
It's 1/4. We have 4 labs. Experiments.
But that's easy as...
Oh no, the way we do it is not going to be like this.
Oh, yeah.
We're going to take many measurements and put them together.
Thank you.
No problem. No
Yeah,
problem.
that we cannot write a lot before.
Will be a bit hard, yes, indeed. Well, let me just see what they put in as the answer.
This is good.
A ray of light is directed along the radius of a semicircular glass block, and the path and reflected is observed. The angle I is increased until you get 90. At this point, the refracted ray will travel along the boundary between the glass. The paths of the rays are plotted, and the angles at this point is the critical angle. So, the first mark was having a semicircle. Now, in my picture, I didn't quite make it clear. I said the whole thing is glass, but really I don't need the whole thing to be glass. I just need like this to be made of glass. So that would be the diagram I would give myself 1 mark for. Then the next one, the angle I is increased. Okay, so that's 1 mark there. At this point, the refracted ray will travel along the boundary between glass and air. So I drew that in on the picture. So I get another point for seeing that. Or, likewise, because I said here the R is 90. So, whatever way you want to think about it, I'll get 1 more point. And then my last one, at this point, this is the critical angle at this point. So, the critical equals the I. That's my last mark. So, I have my 4 marks here. Yeah. So, not too bad. A little bit to write. Let's have a look at the next one. Here, you're given the critical angle. What is the N for the glass? 2 marks. This is A part 1. Now on to part 2. Okay. Oh, good grief.
So reflected
Well, sorry, I didn't hear you because I was clearing my throat. What did you say?
reflected index of air is 1.
Correct, yeah. There's not, it might worry you to really think about this a lot, but there's not much difference between air and a vacuum. Which of course, should worry you because that's the difference between living and dying. Remember, we said the density of air is only about 1 kilogram per meter cubed. That's not a lot in a meter cubed. Kilogram would be what? 20 bars of chocolate, I suppose. Okay, this should not take you that long because you have a direct formula. The C will equal sine inverse 1 over the N. And is it a 2 or a 1 here?
Yeah, wow.
N1. Well, it doesn't really matter because. Anyways, we can say sine 1 over sine C is equal to the N1. So if I just go 1
over sine C, not sine C over 1.
1 over sine C.
41.
41 point what? Hold on, I'm in the wrong mode. What is it? Oh my god, no, it's 41.81. 1.5. Lee, remember, it's impossible to have n less than 1.
Oh, because I'm thinking and 1 and 2 sine 1 sine 2 then.
Okay. Next.
What?
The glass was placed under water. Now what's the critical angle between the glass and the water? Oh, well that's okay. Sine inverse 1.33 over 1.51. How many marks have they given me for that? An outrageous amount. Outrageous. 61.7. 3 flipping marks. Way too much. So I can do it in on my calculator in one step. No, well, I write this down. Yeah. No, good point though. Now you might be thinking, Stephen, you did that too quickly because you have to think carefully. What's the N1, what's the N2 and all this. And I said, no, I don't. I don't have to think carefully because it can only be this way. It can't be the other way. Mathematically, it's impossible to get the sine inverse if the bigger number's on the top. So I don't even have to think. I just have to remember the only way I can get the sine inverse is if I put the smaller number on the top. So I'll have to think now which is the N1 and which is the N2. So it goes from the more dense to the less dense. So the N1 is the more dense, which is the glass, and the N2 is the water. But I don't even have to think about that. So 3 marks for not thinking. Okay. Now we're on to B, the double slit. So, the first question is basically what is the fringe distance? You've got a formula for that. So calculate it, should only take you a moment. I better plug in the battery. I got Dennis's old laptop fully working, so now today I should start transferring my programs over. Huh? I don't have many programs, but you know, like Dropbox and my graph programs and all this. My calculator. Huh? What again? Cap it? Oh, type it. Type what? Oh, no, I'll just copy it, don't worry. Okay, we got the first one. So the formula is S equals lambda D over D. So what's the lambda here? 438 nano. Oh, for goodness sake. And 0.915.
Yeah.
3.35. I hate when I do that. Start again.
You can undo it.
No, I can't actually. 438 nano times, right, 0.915 over 3.35 times 10 to the power of minus 4, answer 1.2 millimeters. 1.196. 2. You move the screen further away, and the distance across 30 fringes is 40.6 millimeters. How far away have you moved the screen? So in other words, what they're doing now is they're giving you the S. This and this are still the same, and they want to know what the D is now. And they're kind of giving you the S in a sneaky way. They're not telling you the S for 1, they're telling you the S for 30 fringes.
So it's 29.
Yeah, I don't think so. Well, actually, no.
Teacher, I made a question.
Yeah, sorry. I think it's just divided by 30.
Oh, was it? So, But two fringes is only one.
I actually don't know if you had, imagine you just had two dots. Do you call that two fringes or one fringe? Is the,
Two dots.
or maybe it's just one fringe because of the dot to dot. Do you know what? Let me check the marking scheme.
Oh, it's 30.
It is 30? Yeah. Yeah. I don't think they're trying to be that sneaky.
But I don't get it. Fringe is like white, a bright fringe or dark fringe, right? So one fringe is 2 points. So two fringes, whatever.
You know what, Lee? I'd have to actually look up the dictionary to get the precise definition of fringe. Because what you're thinking about is now what I'm thinking about. Is it the thing, the white dots that we're calling the fringe, or the whole unit, a dot to a dot? Is that a fringe? Dictionary, I think, will need to be consulted later. Anyways, no matter. It's divided by 30. Oh dear. I'm going to add in a CD question. That's what I'm going to do. Remember I was talking about the CD, the two lasers? I think I'm going to make that a question and add it to the worksheet for the January students. I think that'd be an interesting question. Yes. Yes, I can see it now. Because you have the laser. The laser has to go through a diffraction grating, split, and then these two bounce and come back up. And if there's a hole, they need to be destructive, and if there's no hole, it needs to be constructive. No, I like it. I can picture it. And I can make it a multi-part question. Yes, there's something nicely. I'm coming for you, Bruce. Right, we got the answer here? Well, actually, the good news for you is, when I print out the worksheet, that question will be in it, so you could try it yourself if you want. But don't worry. I know you were worried that you might miss this wonderful CD question, but you didn't. Okay. I could make it like a student is trying to build their own CD player. Something like this. Right, so, this one here. Firstly, let's get the S, which will be 40.6 millimeters over 30 fringes. What's that, please?
1.353
millimeters. Yeah. Now, using the formula, we have 1.353 times 10 to the minus 3. That should equal lambda. What's the lambda? Well, it's lambda d over d, and this is the thing that I want, isn't it? So I can just say that d is 1.353 times 10 to the minus 3 times the d over the lambda. What's the lambda? 433 nano? 438 nano?
Yeah.
And the d?
3.35 times 10
minus
4.
Okay, so what does this work out as?
1.035.
Or 1.04, whatever. But we have to read very carefully. Is the question how far? Lee, please listen.
Yeah.
If I beat you up, then we'll all need to pretend that didn't happen. You know, but see, I didn't upload it yet. I can edit this. So, you know, when you're talking to police, you can say, and this is the part in the video where he beats me up, and then the video just goes, And then when they're interviewing the other students, like, did you see Lee getting beat up by his teacher? They're like, no. Who's Lee? He's not in our class. Please don't let this happen. Don't let this be you. Okay, now we have to read the question carefully. Is it that they want to know how far away it now is, or how far back it was pulled? So in other words, do we need to take away the 1.196? So we have to just make sure our English is okay here. Determine the distance the screen has been moved. So my question is, should we use this, or should we use the difference? Should we look at 1.196 minus 1.04? And because this number is smaller than this is moved inwards. Huh? Is it? Oh no, I'm looking at what was the capital D?
0.91.
Oh, okay, sorry. So 0.9, and this is moved outwards.
What is 1.1?
No, sorry, that's wrong.
Yeah.
Sorry.
1.04.
1.035 if we want to be a bit more accurate here. Right, so guys, what do you think? Are we using this? Or are we using this? A or B? I think because it said the distance has been moved, I think it's this. So what is this difference here? Moved out 12 centimeters.
Yeah, how can we know it is moving out of this?
Because this number was bigger than this number to begin with. Let's actually see what the answers say. Yeah. Right. What is coherent?
Same word as
Me.
Well, let's use the right vocabulary. Please stop saying words and give me a sentence with a verb. What's a word? Yes, Monica? Two waves are coherent if they have constant phase difference and same wavelength. They just have to say constant phase difference. I'm pretty sure, well, maybe we don't need the wavelengths to be the same, but for this Young's double slit experiment, the wavelengths are the same. In fact, because you're using the same wave and you split it into two. Maybe it's expecting too much for the wavelengths to be the same. Can you Google search coherent waves, and we'll just double check this. Yeah? Go on, Monica, what's the sense?
Two waves sorted by perfectly coherent if they have a constant phase difference in the same frequency and the same waveform.
Yeah, now the same frequency would mean the same wavelength if they're both travelling at the same speed, which in this case is the speed of light. But I wonder if the slight difference in the definition is because they said perfectly coherent instead of just coherent. Is there a definition for just coherent and not perfectly coherent? No? I would like to say the wavelengths are the same. Or at least
in another they say it just means a constant phase
you know what? Maybe that's it. If they're perfectly coherent, the wavelengths are the same, and just coherent means... I'll have to double check this in my physics book.
What if it is not perfect?
Most of them are saying same frequency.
As well, yeah? Or which would mean the same wavelength for the... Okay. I am happy that the answer I feel like should also say then at least same frequency or wavelength. Anyways, a diffraction greater than 800 lines, a ray of light of wavelength 438 is incident normally on the grated surface. Okay, part 1 we can easily do on our calculator. What's the D? It'll be 1 over... Come on, dudes. 1 over... Well, what's happened to my... What's happened to my mouse? I can't click anything.
It's time to let it go.
No, it'll come back, don't worry. Okay, it's gone. 1 over, type it this way, 800 times 10 to the power of minus 3. No, that's... Oh, no, sorry. No. I can't convert it. Can someone type it in, please? Can someone type in 1 millimeter over 800?
And what you want?
1.2,000.
Oh.
1.25 micrometers. Okay, part 2. What's the D? Part 2 is what's the angle for the second order? Okay, calculate that, please.
But how did you know what is 800?
It means if you have 1 millimeter, there's 800 lines. So the diffraction D, the distance between the lines, would be obviously 1 millimeter divided by 800, because it's 800 per millimeter. What's the answer for number 2, please? 44.5? Okay, and finally, number 3. What is the maximum order? So, that's the same thing as we did earlier. The formula is straightforward. Okay. We got an answer here. What's the n? 2 only. What was it? It was 2.85. Okay. Let's check the answers here. 2. Correct. 44.5.
Correct.
Yeah, and then
Correct.
alright. This is a pretty good waves question. Nothing peculiar or difficult here. Careful now. What are you whispering about? It's about me. What? I don't know what you're talking about, dude. Alright. Let's see. Mechanics, materials, fields, no, waves, atoms. Guys, let's look, guys. I don't want to do all of this question. I just want us to look at it together and just say which formula is required for each part, or what the definition is, okay? So the first one, what is the difference between polarized and unpolarized? Yeah, well, like, how would you explain that? Yeah, but in the exam you can't write just this.
It allows one direction from the other.
Yeah, but we need actual.
It converts.
That's the key word. The key word for the polarizing definition is plane. So a polarized wave is one which is propagating in one plane only. Yeah, but not quite. And an unpolarized wave is a wave which is propagating on many planes. Okay, so the key word is plane. This will help you write the definition. Are we okay with that? Yeah. What type of wave vibration can be polarized? So which one can be polarized? Transverse or longitudinal? Transverse, yeah. Light of that frequency is put through a diffraction grating, and the second order is 43.5. What is the number of lines? Yeah, so basically the question is a sneaky way of asking you for what the D is by using the standard formula n lambda equals d sine theta. But then you don't just give the D, you have to convert it back into number of lines. So for example, if you got the D is, I don't know, 0.6 micrometers, you would have to just get the reciprocal of that. So you would do 1 over 0.6 micro, and that's how many lines you have per meter. Yeah, like for example, let's say you got an answer of D equals 0.6, or let's just make it easy in my head, 0.5 micrometers. Then the N would be 1 over 0.5 times 10 to the minus 6 lines per meter. So that would be 2 times 10 to the 6 lines per meter.
Millimeter.
But if you want to do it in millimeter, then you just divide this answer by 1,000. Did it ask you for millimeters?
Yeah.
Oh, those sons of a gun. Right, so that would be 2 times 10 to the 3 per millimeter, as an example. Okay. Well, that's easy peasy for 2 marks.
Teacher, why is it decreasing from meter to millimeter? I thought it was increasing. Line from meter to line from millimeter.
Yeah. If you have 800 lines in a meter, then you've got to have less lines in a smaller amount of a meter. If you have 800 lines in a meter, how many lines do you have in half a meter? 400.
Yeah.
Decreasing.
Yeah.
The next one, what's the angle of the third order? Which formula is that?
And lambda b.
Yeah, and again, that's easy peasy. Explain why we can't see the sixth order. The maximum is probably 5, which we would have to calculate. An experiment to show the two-source interference of sound waves. Yeah, but we just need to experimentify that picture. So we can't just say, stand the boy walking down the hall between two speakers. So if you want to sort of experimentify this, I realise I'm just making that verb up. How would you experimentify this question?
Speaker.
Good, we can replace a room with a box, yeah. Yeah, good, instead of doors. Good, okay.
And then make a voice detector.
Yes, not a voice detector, but a microphone.
Oh, okay.
So have the microphone slide across the back of the box and record. And when you play the recording back, you'll see the peaks in the volume. So,
Can't we just use humor? I mean...
No, because this is physics, not biology. We need to measure things, okay? We can't ask people how they feel. Right. In Young's double slit experiment, laser light of this wavelength is shown through slits which are this d apart, and the interference fringe are the distance between the grate and the screen is 0.95. And so the first question is, what is the distance between 25 fringes? Well, you will have to work out the fringe distance and then multiply that by 25.
Oh, 24.
I feel like they'll use 25 in the marking scheme. Yeah?
Yeah, that is 24. 25. For two bright fringes, we have only one F. So 25 has 24.
Let's check the marking scheme.
I mean, you mentioned here bright fringes.
You can see.
What's that?
Ghost.
No.
Couldn't be now, it's only 10:37. I'm nearly finished. Right. You are committed to 24?
Yeah. You
You're-
mentioned bright fringes. You mentioned it. Yeah, the bright part.
Dun 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 dun.
But teacher, I don't get
Dun
it.
dun dun dun.
The as is the bright, right? It's not
I
bright
told
or
you
not.
we need to check the dictionary.
The as is bright.
Yeah, well hang on. Wait, listen. Listen. Just because it says bright fringes, the bright might not be indicating two. Bright dots represent one fringe or two fringes. The bright is just telling you that you're looking at the bright spots to bright spots, not dark spots to dark spots.
Yeah.
In other words, I don't see how just because they use the word bright that guarantees in your head, oh that means must be 24 then. Because listen. We haven't checked the dictionary yet for the precise meaning of the word fringe. Is fringe the name for the length, the piece between the dots, or are the dots themselves called fringes? This is what you haven't checked yet.
So if it's a picture in 25 and it's a dot in 24.
Yeah.
The order is 20. No, the order would be like 12 because it goes to the minus.
No, we are not saying about the
Yeah. No, but what I'm saying
There's a lot
is
of things.
the word fringe refers
Yeah.
to a fringe is a bright spot to a bright spot. I don't think this is called two fringes.
Okay.
Now that's what I think. You have the definition there. Read it aloud, please.
It's a bright or dark band called
That's the key word, band. A
What
fringe.
is band?
Fringe is a band, which is like a rubber band,
Yeah.
interval. So one fringe is one band, which is a dot to a dot. Yeah,
It's a dot to the dot.
it's a fringe.
So that's very
Yeah,
hard.
Oh, so two bright spots is a fringe.
Yeah,
Oh, okay.
yeah.
So
Okay.
that's
Now, describe how the pattern changes if the following happens. One of the double slits is covered over. Oh, interesting. You cover one of the two slits. What happens to the fringe pattern?
No interference.
Yeah, but like, okay,
Light.
no. Picture this. You have the light, it splits between two slits, and you get a fringe pattern. Dot, 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 dot. You cover one of the slits, and the light only goes through one hole. What do you see on the screen now?
Bright spot.
No fringe.
A line.
Yeah, what do you see?
Just light, but decreasing the intensity.
Yeah, a single dot that is brightest in the middle and dimmer at the edges. Now, I don't think it's going to be that spread out. Lee,
Okay.
my patience is being tried. The next one.
I had chocolate.
The screen is moved closer to the slits. What happens to the fringe pattern?
Increasing. Wait.
They no, the D is getting smaller, so the fringe pattern, the fringes get closer together. Because remember the formula.
Yeah.
It's S equals lambda D over D. If this is decreasing, then this is decreasing. So the fringe pattern, the distance between the bright spots reduces. And lastly, the light source is replaced by a laser light of a shorter wavelength. So in other words, you reduce the wavelength. What happens to the fringe pattern?
Decrease.
Again, the distances between them decrease because the angles all decrease, because we said a smaller wavelength makes a smaller angle. So again, waves can be a good question in the exam. The only time it's hard is when they have, I think, the standing waves with, you know, the example I did of the radio tower. That was a bit tricky, and also the end correction's a bit tricky as well. But a question like this, how many formulas did you need to know to do this entire question? 2. Now compare this with the mechanics question, which could have like 5 or 6 or 7 formulas in it. But for waves, in the whole chapter, there were 2 formulas. The whole chapter. So what's good about the waves is there's not much calculation or maths problems in it. No, I'm sorry, that's not true. There were 3 formulas in waves. We have Snell's one as well. Okay. So anyways, I think when we get closer to the exam, we'll talk about which are good questions. So if you were looking at this paper, you have to do 3 questions. I think the waves would be good to do. That's 1. We haven't done this yet, but the atoms is always a good one. This is the fields one, which this is atoms. This one is materials. This is a good one.
Yeah,
Materials is good. And this is mechanics.
Yeah.
This is a mechanics which you might screw. It's not too bad, but it's a projectile, and it's a projectile where it's landing on a. It's like the one on a cliff. It's the S is not 0 at the end. Although it's actually okay. This materials one is okay. So when I look at these exams, I think, yeah, all these questions are okay. My students should do well, and yet my heart breaks every year.
But the style is different. It's like the word guy. Yeah.
Wordy guy, yeah. Have I got an example of Wordy Guy's exam? I do. Here is his end of semester 1.
Gosh. Bye-bye.
That's not too bad. Let's have a look. So the first one is... No, before you freak out, the first one is all just about vectors. What is a vector? Yeah, 1 mark. What is the magnitude?
The first one has freaked me out.
But these are all easy, like, what is the acceleration? So that's v minus u over t. What is the momentum? That's mv. What's the force? That's mv minus mu over t. The delta p over t. You know, this one here, a steel ball is released from rest at the surface of oil. Describe the motion you would expect to see, and explain this in terms of forces. So it's well, yeah, it's slow at the beginning, and it speeds up, but then it doesn't continue to speed up. It will reach a maximum velocity called the drag velocity. What is the cause of this? At the beginning, the force of gravity is constant. The drag force begins at 0 and increases until it equals the weight, and then this is terminal velocity. And the reason the drag force increases is because the speed increases. Yeah, good. Part 4 is a Z. I'm not going to tolerate an interruption again, especially when I'm sick. Okay, because my throat is sore, so every time you stop me, it makes me say extra words I don't need to say. Okay. Number 4, conservation of momentum, and then we want to know if it's elastic or inelastic. Do we gain or lose energy? We already know. We already know what's going to happen. Well, no, actually, the lorry could gain kinetic energy. It depends on what hits it. And sorry, it's not elastic or inelastic. That's the total energy. Forget I said that. Yeah.
So I think.
Huh? I don't know what it is because the lorry. Oh, it's not a collisions one. I'm sorry. It's just going along a hill, is it? Yeah.
So what is it?
A lorry drives along a road and it climbs a hill.
Loss.
Is there gain or loss of energy for the lorry?
Neither.
No.
It's just conversion from kinetic to potential.
Well, the problem is this. It does not tell you if the lorry is going faster or slower at the end. So, it could be a conversion, Lee, if at the top of the hill it's going slower, because as you said, the kinetic energy is turned into potential energy. And I think that's what the answer is here. Yeah,
That is easy.
that's just MGH. And the second part is making you think, where did the MGH come? I know! I think he's trying to be sneaky here and is looking for you to say no change, as the potential energy gain came from the kinetic energy's loss.
So what is it?
No change.
No change.
Well, no change. But if you absolutely forced me to pick a gain or a loss, if I said it can only be one of them, then I would have to say gain. Because what would happen is, at the end, the truck is going at the same speed because the person put his foot down more. So the truck has the same kinetic energy, but it also now has potential energy as well. Now, it gets a bit complicated because you can say, well, it's a gain, but that's only because he put his foot down and he got energy from the conversion from the petrol. Really, there's no change. But if I have to pick one, gain. Because the petrol is in the lorry. It's not coming from the outside. 5. What type of problem is 5? Lammy's three forces. Because there's three forces here. So this weight force, which should be somewhere like here, must point towards the weight force here. Yeah, straight down. And they want you to find T1 and T2. But actually, do you know what? Another way you could do this. Forget about this. Just look at this. I think this is the distraction. If you just focus on the hook, how many forces are acting on the hook? T1 going out from the hook, T2 going out from the hook, and a reaction going up from the hook.
And the weight?
No, because we're not looking at this. We're only looking here. And Lammy also said 1 Newton over sine 90 equals T1 over sine sine 150 equals T2 over sine 120. So I have enough to get T1 and T2. In fact, this is using Lammy's theorem, you can get your 4 marks quite quickly here. because they nicely provide the 1 Newton reaction force here, which means the weight of this was 1 Newton, because this is on a weighing scales. So that's a good one. 6 is circular motion. It's a bit tricky. This actually is kind of a hard circular motion one. 7, well, I know it looks long, but this is just the pendulum. What is the amplitude and, define amplitude. What's the time? Well, that's 2 pi root L over, oh no, we have the F here. The T is 1 over F. 1 mark. What is the maximum acceleration? The acceleration equals minus omega squared x. The biggest x can be is A, the amplitude here. We know the amplitude already, we just need to know the omega, but what's the formula for the omega? 2 pi f, yeah, 2 pi over t. Remember we have to sketch the energy graph, so do you remember the potential energy goes like this, and the kinetic energy goes like that, and so on and so on. 8, this is your temperature and your time, and here the temperature between A and B is not changing, even though more time is passing and more energy is going into this material. What's happening? Well, the material is changing state. So here it's going from a liquid, a solid to liquid, and here it's going from liquid to gas, yeah. 3 marks. Explain why the slope is different here and here. Well, it's because the specific heat capacity is different. So the specific heat capacity for this material must be higher when it's in a liquid state than when it's in a solid state. So more energy and hence more time is required to increase it. This is Young's modulus question. And this is a question about the ideal gas law and the proofs we did in that lesson. Knowing the temperature represents the average kinetic energy. Yeah, well that's what they're asking you. The molecule is 40. They have twice the energy as twice the kinetic energy as molecules at 20 Celsius. What is wrong with this statement?
It's correct.
No, it's not. It's not correct. The temperature.
Oh, it is not twice, because we have to consider K, not degree Celsius.
Correct.
It is not twice.
It's not in Kelvin.
Yeah.
It's in Celsius. We only use these laws in Kelvin because 0 Kelvin represents 0 kinetic energy. So 20 to 40 Celsius is not a doubling of the temperature in Kelvin. It would need to go from like 250 Kelvin to 500 Kelvin or something like this. Then the kinetic energy has doubled. So what's wrong with this statement is the wrong units are used for the temperature. We have to use what's called an absolute scale, an absolute temperature, not Celsius or anything else. Draw a circuit diagram which would let you find the IV characteristic of an LED. So do you remember this is the circuit diagram where you have an ammeter, a voltmeter and a variable resistor, and you change the variable resistor and then you can plot the I and the V, and remember the voltmeter is around a fixed resistor and you're plotting the IV for this fixed resistor, and the shape depends on the material. So for an LED, do you remember what the IV graph looks like?
Yeah. For positive it goes up, and negative it goes.
I think for the LEDs, yeah, usually you can't pass the current through backwards. So you get a very high resistance and then it breaks. So it kind of has a straight line on the right, and then on the left it has a straight line that's quite shallow, representing high resistance, and then it must, I can't remember what it's called, some sort of cascade effect. Then all the current flows through at one point, and then the resistance drops off, yeah. I think this is for LEDs, yeah. Okay, and then lastly, this is the question which I had in the worksheet, and what caught me out, Can you remember what mistake
Oh,
was
yeah,
made here?
you can make this series.
Well, which is it? Is this when when B is closed and A is open? B is closed, A is open. Series or parallel?
Series. I know the answer is parallel, but now I'm still thinking of series.
It's parallel. Originally, I thought it was series because I was picturing it as a loop. It's actually still on a straight line. But no, it's as it looks in the picture, we consider it still parallel. So the key is that it's parallel. This will help you out here. No, it's not a line. True. No, face it. And this we haven't done yet. Okay, anyway, we'll finish there. I think I'll have you after lunch. We'll have a look at the coursework for maths after, I think, did you say you wanted? No, we have to do Simpson's rules. Yeah.
Simpson. Simpson.